Okay, class. Today in this lesson we'll be learning how to factor polynomials. Why do we want to factor polynomials? We want to factor them because we want to be able to solve polynomial equations. We're going to be looking at 4 different ways of factoring. We're going to learn how to choose and then perform the different methods. Okay, let's look at factoring again in terms of solving quadratics. Here was an equation. X squared plus 6x is equal to 7. We set it to 0 on one side. Don't forget to do this key step here, setting to 0 on one side. We did that, and then we factored it. When we factored it, if it was factorable, not always factorable, but if it was factorable, the key thing was we were able to then consider 2 different solutions. When the left-hand term was 0, or when the right-hand term was 0 right here. If either of these are 0, then this multiplies out to 0. That's why we want to set it to 0 on one side. Okay, don't forget to do that. In this case, we have 2 solutions, -7 or 1. Now, with polynomials, it extends. The same concept extends up. So let's look at a cubic polynomial. We have equals 18 on one side. Get rid of it. Make it equal to 0. There we go. And so now we have this polynomial. Now let's see if we could factor it. We don't know how yet, but this is just assume you kind of know. And this is our factored kind of form of this. Now, same way, we set each one of these factors to 0, and then we just have a simple linear equation here to solve, and we find out that x can be any one of these 3 values. So now the key step, or the key idea here, is if we can factor, we can solve. So how do we factor? That's the lesson for today. There are 4 different ways that we're going to learn how to factor. We want to be able to factor it completely, meaning we don't want to be able to factor it anymore. It cannot be factored anymore with integer coefficients. Let's just kind of think for a moment with numbers. When I had a number like 210, we factor this down, divide both sides, divide it by 2, we get 105. But we can keep on factoring this, right? This gets factored out into, say, 5 and 21, and this can be factored down to 3 and 7. So these are kind of the lowest factors. We want to do the same thing with polynomials, bring it down all the way to the smallest factors that we can find. We have 4 different ways: common factor, special patterns, grouping, and quadratic form. Let's look at each one of these one by one. Common factor. This is the one that we always start by doing it first, if possible. This will make our lives easier. So, when we have something like this, there's a common factor of x in each one of these. Factor it out. In some ways, it's kind of like the reverse of distribution. Let's factor it out of each term. The x cubed divided by x is x squared. 3x squared divided by x is 3x. 2x divided by x is 2. Then we could keep on factoring, or we could try to keep on factoring. In this case, we can. So don't stop. After the first step, maybe it exposes more that you can do. Here's another example. Let's look at the numbers first. 2 and 18. There's a common 2 in both of them, so I can factor out a 2. I know that. Now, let's look at the x terms. Well, I have x to the 5th, x to the 3rd. There's x to the 3rd that I'm going to be able to factor out. So now, let's just do some thought experiments of when I factor it out. Basically, what I'm doing is I'm dividing each of these by x to the 3rd. And so I have x squared minus 9. You look over here, if I divide these, this would become x, x to the 5th divided by x to the 3rd is x squared. And this reduces down. The x cubes kind of reduce down to 1. 18 divided by 2 is 9. Okay, so don't stop here, right? This is a special pattern. X squared minus 9 is x plus 3, x minus 3. Okay, so give these a try. I'll let you work through these, and then we will continue on. Special patterns. Second method, after we've done common factoring, we look for special patterns. Actually, we did that over here. This was we factored out whatever was common, the 2x cubed, and then we noticed, hey, I have a difference of perfect squares, and then I broke that down. Same idea over here. We have the difference of perfect squares being the number one pattern you should memorize. Here are two more. These are two more that I'm going to introduce. A difference of perfect cubes and the sum of perfect cubes. These are its factors here. So, yeah, you're going to need to kind of memorize these. But it's good to know that a cubed minus b cubed is factorable. Same with a to the third plus b to the third, that it's also factorable. This part's easy to remember because, you know, the a minus b or the a plus b part, this part's a little harder to memorize, but you can actually do synthetic division or something like that if you forget what this expands out to. If you just remember that this part is, you know, a to the cube minus b cubed has a factor of a minus b, then you could figure out this other one. Okay, this special patterns, whenever there are two terms, you can possibly look for the special patterns, one of these three. So let's look at this. X to the third plus 64. 64 is a perfect cube. You should start learning perfect cubes. So let's just kind of work out a few here. 2 to the third is equal to 8. 3 to the third is equal to 27. 4 to the third is equal to 64. And we'll do one more. 5 to the third is equal to 125. These are good to know. When you see these numbers, think perfect cube. Okay, we could use our little template here. We know that the sum of perfect cubes is a plus b times this. So I'm going to put this down here as a little template. And now this is our a, this is our b. We just kind of stuff it in. Okay, that's how we expand there. Let's do one more. Here, you know, nothing pops out right away. These don't look like perfect cubes. They don't look like perfect squares. But remember the first step, always to look for common factors. So I'm going to factor out a 2x squared because they're both divisible by 2. And also there's an x squared term in both of them. When I do that, 16x to the fifth divided by 2x squared is 8. X to the third. And then 250x squared divided by 2x squared is equal to negative 125. And now we realize, hopefully, just looking down at this again, this little thing we made, 8 and 125, 8 and 125, those are perfect cubes. So I have 2x to the third minus 5 to the third here. So that's like my a to the cube minus b to the cube pattern. So I'm going to put down, you know, just write this out down here as a reminder of my template. And now I'm going to stuff in my a and my b into that. And then I'm going to multiply it all out, and I get this. Okay? Special patterns. Next, let's move on to grouping. Grouping is done when we have 4 terms. Here's an example. What we're going to do is we're going to take the first 2 terms and factor out whatever we can. I see a x squared term in both of these. Let's factor that out. Next 2 terms, 16x plus 48. I see a common 16 in both of these. Let's factor that out. That becomes x plus 3. Now, kind of the convenient thing here is that x plus 3 is a common factor in both of these 2 terms. So I could factor that out as well. So let's kind of consider, let me just kind of highlight it like that. And so we have our x plus 16 that is remains once we pull out or distribute out or factor out the x plus 3 here. Okay? Nothing more we could do. We can't factor this anymore. It's done. Let's do another one. Same idea, but we're going to find out. There's a little something tricky when we have the minus sign there, so be careful. Okay, first 2 terms. We have a common x squared term here. X plus 7 is whatever's left over there. Now here, I'm going to factor out a minus 9. When I do that, I get an x here. But notice, minus 63 needs to be divided by minus 9 to get plus 7. Okay, plus 7 there. And notice, yeah, you got to be careful with the signs. Notice that we do have this common x plus 7, x plus 7. Now, let me say that this method of grouping doesn't always work. If you get two different things here, you're done. You can't factor it anymore. Grouping works when we see these common factors appear. Okay, so now we can continue on one more step, and we can factor out the x plus 7, and we're going to be left with this x squared minus 9 here. But we don't stop. This is a special pattern, difference of perfect squares. We can expand that out, or factor it out, sorry, to x plus 3, x minus 3. And that's our final answer there. Okay, last method, quadratic form. Quadratic form, we look for 3 terms. Why 3 terms? It's called quadratic form because we're looking for a quadratic signature. Kind of this ax squared plus bx to the first plus c. Now, you notice here with the typical quadratic form here, standard form, we have a power to the, x to the power of 2, x to the power of 1. So we're going to look for something with this kind of 2 to 1 relationship. Here we have x to the 6th, x to the 3rd. It has this signature of a 2 to 1 relationship. So I'm going to do this. I'm going to say let w is equal to x to the 3rd right here. And now I'm going to substitute. So when I substitute x to the 3rd with w, this just becomes w. When I substitute w with x to the 3rd, x to the 6th becomes w squared. Now it looks like a nice little quadratic here, and now I could think, can I factor it? Yes, I can. Oh, wait, these need to be pluses. I have a mistake in my notes. Okay, so now it's factorable. We have w minus 3, w minus 2 is equal to this up here. Don't stop. Let's do one more step. Let's substitute back the x cubed for the w, and now we're done at this point. There's an opportunity. We have a perfect cube here, but there's no perfect cube here. If there were, we would use our special patterns to then factor this some more. Okay, let's look at one more. This one here doesn't look, it has this m squared term, but the normal pattern is we expect a constant here. So right now it's not quite in this quadratic signature. 6 to 4 is not a 3 to 1 or 2 to 1 type of signature. But we could factor out the m squared here from every one of these, and now we're left with 36m to the 4th plus 12m squared. Now we have this 2 to 1 relationship right here. So I'm going to do this. I'm going to let w equal 6m squared. And the reason I do that is I notice that this is a perfect square as well, so why not take the opportunity to do it at this time? I don't have to do it. It's possible if you were to just substitute like this, just as we did in the above example, it'll work just fine as well. I'm just showing this alternative method. So now I substitute the 36m to the 4th substitutes into or becomes w squared. 12m squared becomes 2w instead. Now I could factor this down. This becomes w plus 1 times w plus 1. But let's push back in, substitute back in the 6m squared here. And now we have this m squared times that. Okay, so that's the lesson on quadratic form. Now, on the next page, I have a bunch of problems for you to try out. Oops, I showed you kind of the answer for this one already. Go ahead and do the rest of them. I'll show the answers in 3, 2, and 1. And on the next page, there's some more questions that you can try out. Oh, there's the answer for that one as well. And here's the answer for the last one. Okay, have a good day, everybody.